Alrighty. Let's go ahead and get started here. Alrighty, we're going to be talking today more about our best friend, again, cyclohexanes, and its various conformers. So, cyclohexane, we talked about the chair. Ooh, that's one of the uglier ones I've ever drawn. Let's try that again. There we go. We remember we have chairs for our cyclohexanes. Our best friends typically is the main conformation that we get. We can see kind of what this looks like. I don't know why I'm drawing the H. If we want to take a look at it in a what's called a double Newman projection. So Newman projection, remember, we're looking at along a single bond, and we're going to go ahead and look at what's happening in between them. If we take our eyeball and look along these two bonds simultaneously, so this one and this one will be on one Newman projection. And then if we look on the second bond, we can see what this is going to look like. So we can draw two Newmans. If we see here, our two kind of like front carbons have a carbon in between them, a CH2. Good morning, Lefpreet. And then we have the back carbons also have a carbon in between them. And we'll see that the rest of the stuff is just hydrogens. So this is what's called a double Newman projection. And we can also use it to kind of evaluate the relative stability of different conformations. And so the chair, we end up with everything nicely staggered. So we have our kind of, all of our things here are going to be staggered, which is why the chair is good for us. And so in this chair conformation, we end up getting all of our hydrogens to be staggered from each other. And as a result, we're going to have kind of all favorable interactions happening here. And so with these kind of double Newmans, we can just kind of see how that's the case. We can see that all of our hydrogens are staggered. That's a good thing. We have kind of our lowest energy. And we're going to see that, the cyclohexane can flip, right? If we were to flip our cyclohexane, we would just rotate some of these. We would essentially rotate our front carbons and rotate our back carbons at the same time, just to illustrate kind of how a chair flip happens. What that's going to look like. Actually, let me do this one horizontally. So I'm going to have our original chair here. And let's do the chair flip side by side so we can see it. Oops, that's an orbital. What is that doing here? Okay, we must try again. Alright, so here we go. By the way, although it may not seem it, I'm going to just note that everything that's pointing up and down with these is going to be our axial stuff. Everything that's pointing to the side are our equatorial things. So, for example, if we just take a particular hydrogen, this one, I'm going to label it HE, it's an equatorial hydrogen. So, and let's go ahead and see what happens when we rotate this. So, if we want to do the chair flip, we're going to rotate kind of all of these things. So let's rotate our front carbon carbons, and we're also going to rotate our back carbons the opposite direction. So I'm going to rotate the back carbons the opposite direction here. If we just look at the front carbons, if we rotate those both kind of disrotatory from each other, if we rotate them one clockwise, the other counterclockwise, we're going to end up now with our carbon in the middle is going to be up top. We're going to have rotated our hydrogens. And we're going to end up doing the same thing here. So just looking at the front carbon right now. This was our equatorial hydrogen. Or let's just say, yeah, fine, whatever. This one is now in an axial position as we've rotated it. So we've just flipped our chair. This is now an axial hydrogen. So what used to be an equatorial hydrogen becomes an axial one. But notice it's still pointing down. So this is just the same thing as before, but everything's going to be pointed the opposite way. And if we draw the back carbon stuff, we're going to see that now we have that one, everything's rotated as well. All the axial bits became equatorial bits, and all the equatorial bits became axial bits. I've kind of drawn these CH2s badly. I really should draw one up and one kind of down. Go away. But that's more what those look like. And so we still have this axial and equatorial on those ones too. I'm just going to not draw them for our flipped one. But the point is, when you do a chair flip, all that's happening is you are taking everything that was axial and making it equatorial, everything that was equatorial, making it axial. So you have these kind of choices. You can choose which conformer is going to be more stable than another. In this case, they're the same because they're just plain old cyclohexanes. So let's go ahead and kind of take a look at a few examples here. Let's see what it looks like when we have two methyls that are essentially what we might call cis to each other. We're going to learn next chapter how to make this a little bit better, because we don't often use cis and trans with this sort of stereochemistry, as we'll see. But for right now, that's kind of our only way to describe their relationship to each other. So they're both pointing up, we could say. They could both be pointing down. Doesn't matter. If we draw a particular chair for them, we can say that this green carbon here is the carbon we're looking at. We can say that, just so everything's super easy what we're talking about. If I've got to put my methyl groups up, the first one is kind of the easy one. That's going to be an axial position. Remember, on the next carbon, though, the one that's pointing up is equatorial. So let me take another moment to kind of refresh our cyclohexane dreams. Oh gosh, this is even uglier. That's never the way I draw them. Okay. Nope, that's not good either. I need more space in between them. Good enough. I'm terrible at drawing these, but I'm just terrible at drawing in general, right? Everything that's pointed up, I'm going to draw in light blue here. And, obviously axial. So these are all of our up positions. So, relatively speaking. So, all our down positions are kind of the opposite. this one is going to be straight down, and for that one it's going to be the opposite. It's going to go, oops, down that way. Yeah, just have Kevin draw them. He's probably better at me than this. This one should be pointing down more, not straight out, but there we go, kind of, because I'm not very good at drawing, but there we go. So these are our kind of down positions in green. We have 3 ones that are straight down, and then we have 3 kind of equatorial down positions. With the up, we have the same. We have 3 up positions that are axial and 3 up positions that are equatorial. These are our equatorial ups. These are our equatorial downs. So all the others are our axial, right? The straight up and straight down ones. So with this particular one, if we're looking at these 2 bonds here, they're both pointing up, right? They're both blue bonds. But we have 1 axial and 1 equatorial. We have 1 equatorial methyl group. So not so great. Let's see what happens if we flip it. If we flip this thing, it's essentially the same thing. We're now looking at, this is now our green carbon right here. We've flipped it down. We still have to have our groups pointing up, right? So there's still going to be blue lines. And so we have our other one now here. If we look at those, we have one that is axial, which is the left one, and we have one that's equatorial, right? So in this case, we still have 1 axial CH3 and 1 equatorial CH3. They're the same, essentially, right? There's no difference. We have 1 axial one, 1 equatorial one. These would be of equal stability. So both conformers here, the one that's flipped and the original one, they're equivalent to each other. So if you were to kind of decide a proportion of which one's which is the more likely one, they're about 50-50, right? They're equal. They're equally stable, so we're going to have half of them that look like the top molecule and half of them that are going to look like the bottom molecule. There's going to be flipping in between those. And so we saw that even with just substituting 1 methyl group for 1 hydrogen on cyclohexane, so just methyl cyclohexane, we saw that we had 95% of the molecules had the methyl group equatorially, right? There's a very strong preference for that. In this case, we don't have a choice. One's axial, one's equatorial. There's no way to do that. And we're going to see this will be the case for all cis 1, 2 disubstituted yeah, that looks right, cyclohexanes. You are going to always have 1 axial, 1 equatorial. I'll even write it out. Equatorial. Remember, equatorial is our happy one. Axial is our bad one, because axial things bump into each other. Right, those 1,3 diaxial interactions that are not so great. So we're always going to see that's the case. If we take a look at maybe a cis 1,3, we can see what that's going to look like. Or you know what? Let's do another example here. Have we talked about bulkiness of like various groups, relatively speaking? Like what's bulkier than what? I don't think we have. Let's talk about bulkiness. So various substituents here. So if we're going to think about what's the... Okay, but I don't think we've like done them in like what's the bulkiest, what's the least bulky, that sort of thing. At the end here, hydrogen will be our least bulky. And our biggest one is going to be our dear friend T-butyl, the T-butyl substituent. This is our bulkiest group. So, because sometimes in this case we had dimethyl cyclohexane, right? They were the same group. But if one of those was an isopropyl group, we're going to see that that's going to be more bulky than a methyl group, so we need that isopropyl group to be equatorial. And so we'll see what those are going to look like. After that comes our dear friend isopropyl. So a T-butyl group is our kind of biggest bulk. Then we'll have isopropyl. Substituents. After that, we can go ahead and throw our dear friend benzene in. So a phenyl would come next. Then we can talk about just kind of, I mean, it's hard to say, you know, ethyl and propyl, pentyl. At some point, the chain length doesn't matter, but just kind of other alkyl, whatever, however long this happened to be. Because the longer you get it, more stuff is just farther away. It's less relevant. We're still dealing with carbon substituents here. However, we're going to say that methyl will be a little bit smaller than those other alkyl groups, like ethyl or propyl. Sec-butyl, we don't really see it as much, but that's going to go in the same category as like just slightly above isopropyl. Because sec-butyl is the same thing as isopropyl, except now we've stuck a extra carbon on it. So it's going to be slightly worse than isopropyl, but better than T-butyl. Better than tert-butyl. So here, we can even put it in, fine. There's our S-butyl. Sec-butyl can be right there. Again, less common though as a substituent. Okay. Over here now we're gonna have, say, like hydroxy, or you know, just kind of 2 atom. The methyl group will be 3. I mean, we can say that here. Sorry, let me add. We've got now 4 atoms, 3 atoms, 2 atoms. Remember, it could be SH instead. We're just kind of looking at the number of atoms. And then we've got other, like, kind of substituents here, like chlorine. Those would be on the smaller side because they're just 1 atom. If you're comparing, say, a chlorine versus an iodine, at that point, since they're both 1 atom, that's when you'd say, okay, well, iodine we know is a lot bigger than chlorine is, so we're going to say iodine is the bulkier of it. But something like an OH is going to be probably bulkier than iodine is, because now we have 2 atoms. And so that's when we start worrying about these things. So hydrogen's our smallest, then any 1 atom substituent, then 2 atoms, 3 atoms, 4 atoms, and then we start getting into more complicated substituents. If we really wanted, we could put cyclohexyl between phenyl and isopropyl, but let's not worry about that. That's, again, less. Cyclohexyl, cyclohexane is not as common, right? So that's kind of our bulky to small things. So if you have to put something axial, make it a smaller one. That is going to be preferable. You want to put your bulkiest group equatorially. This is also the same for like the those Newman projections you did with just linear alkanes. When we're talking about like syn-eclipse things, those are always your 2 bulkiest groups that are together. So this bulkiness chart still works for regular old alkane conformational analysis. So looking at those, it works. By the way, we do have some kind of common abbreviations that we might use when talking about these. So for when we're looking at conformations, so that's either those rotational ones like the Newman projections we did last time, or these chair cyclohexanes, we use abbreviations for your substituents. Because oftentimes when you're drawing a Newman projection or a double Newman projection, if you start drawing like, you've got this and then you've got, I don't know, things get very messy if you actually start drawing in like substituents. So what we often do is just use abbreviations. So we might say something like this, just to kind of keep our focus on the Newman projection carbons that we're looking at, and so we just use abbreviations to make things easier for ourselves. It's pretty common. Okay, so just putting those back. So the T-butyl group. This is abbreviated T capital B U. These are the abbreviations. You would say this IPR. For sec-butyl, you would say SBU, but again, not as common. Let's see. Methyl is Me. Ethyl is ET. Propyl is PR. Let's see, cyclohexyl is often abbreviated CY. Again, not very likely that we're going to have that as a substituent, but you might see those in like other papers. Benzyl is abbreviated BN. Remember, benzyl is one carbon away from the benzene. So if we were to put that here, it would be probably, I'd probably put benzyl here. Again, we don't really see this as much when we're talking about conformations, but benzyl is a phenyl ring with a carbon in between. So I'm going to just erase that for now, but that's what a benzyl is, remember? So benzyl is one carbon here. That's your benzyl substituent. Phenyl is just attached to the benzene directly. What other abbreviations do we have? I think those are the big ones. So those are the biggest kind of substituents that we have abbreviations for. And so when we're talking about putting things on cyclohexanes, when we're talking about the chairs and looking at which chair is better than another, or if we're looking at Newman projections and looking at those staggered and gauche and all those conformations, we use these abbreviations instead of drawing out the actual substituents. So, for example, for a Newman projection, you might have I guess that needs to be in the front. I don't know, you might just have, just random things like this. And so this is these are terminologies you use in Newman projections and chair conformations. So you see here some of these we just have atoms like chlorine or bromine, and some of them we have these abbreviations for things. Because again, if we're just looking, we know, T-butyl is the biggest group on the front, isopropyl is the biggest group on the back. We are in our anti-conformation right now. And so instead of actually drawing these things out, we use abbreviations. Okay? So just putting that out there. So as we see some of these chairs. So I'm going to just leave this screen on for a sec so you can finish copying them all. and then we can move on. Alrighty. So, let's go ahead. If we're looking at now the trans 1, 2. Actually, no, I want to do another cis 1, 2. Here, and I'll even use abbreviations. No, I won't. I could even leave them like this. Let's compare these two. We'll use abbreviations when we look at the chair. We don't have to use abbreviations for the actual regular line angle structure. So between these two, we have here kind of 1 ethyl, 2 methyl cyclohexane, right? That's our name for this dude. We could call it cis if we really wanted to. We have learned that cis disubstituted 1, 2 cyclohexanes, as in things are related to each other, carbons 1 and carbons 2, that one of them is going to be axial and one is equatorial. From this, we can probably already tell which one is going to be our best chair conformation just by looking at the name or the structure of this. Without even drawing one single chair, hopefully we can tell which... we have 2 possible chairs, right? We have one and the flipped one. One of them is going to be better than the other, right? And the one that's going to be better is going to put our bulkiest group in the equatorial position. So remember, we always want to put your bulkiest group equatorial. So in this case, that's the ethyl group, right? We want to put the ethyl group equatorial, and we're going to have to then put the methyl group axially. So if we want to draw this, if we want to put our ethyl group equatorially, and it's got to point up, we can do that. We can say, aha. We can put our ethyl group equatorially up by putting it down here. As long as we still have that 1-2 relationship, if we wanted to put our ethyl group axially and we'd already drawn our chair like this, we could totally... Actually, we could do it this way too. We could put it there equatorially. A little bit bizarre, but that's the same thing, right? There's still 1-2 relationship to each other, right? So we could do that if we really wanted, but I typically tend to, if I'm looking and the methyl group is up top and the ethyl group is below, like in our line angle structure, I tend to then follow the same thing and put the ethyl group below. Like I tend to do that, but it doesn't matter. You can have your ethyl group pointing up on the other side. It'll just be technically the opposite, but better probably to do it this way. So this is going to be our happiest chair. That'll be our good one. So we're going to end up with a happy situation here. So that would be our most stable chair for this structure. So by just understanding the relationships that a cis 1,2 benzene cyclohexane, is going to give us 1 axial, 1 equatorial, we can see what trans will give us. If we have a trans relationship between them, we can see we're going to get 2 chairs like before. Hey, that one was pretty good. That one's getting worse. These are beginning to look more and more like lightning bolts than cyclohexanes, but that's okay. If we see here, we've got 1 up, 1 down. Oops, I need to draw this one flipped anyway. So, one up, one down. I'm missing a carbon here, hold up. Yeah, whatever. This is so ugly. Let me try this again. Here, I'll try and like mirror image it. There we go. Hey, that's a pretty good one. Okay, so if we look at this, remember the pointy one, pointy up is pointy down now, but things still have to be pointing the same direction. So that carbon, the green one, had an up methyl, so we still have to have an up methyl. Remember, an up on this position is equatorial, and the other one is a down position. And remember that the down position now is equatorial. So they have switch spots. So in this case, we have both axial. And here we have them both equatorial. So the winner shall be both equatorial. Very easy. With a trans relationship, when you have 1,2 disubstituted cyclohexanes, you can have both substituents be equatorial. And that's always going to be better. So you don't even have to think which one's bulkier, just put them both equatorial. And so we can see here we're going to have some patterns. I'm not going to draw them all. You can. You can have fun with them. We can see that if things are disubstituted, we have two things on our cyclohexane. If they are cis to each other, we're going to get one axial, one equatorial. If they're trans, we're going to get both in the same. We can choose. We're going to see it'll now be flipped for 1,3. And it'll be flipped for trans. And then back again for 1,4. So if you can kind of understand this chart here, this is kind of their relationship to each other. So something on carbon 1, something on carbon 2, if they're trans to each other, you can make them both equatorial. It's when you have cis 1,2, cis 1,4, or trans 1,3, those are the times you have to decide which group is bulkier and assign that bulky group to the equatorial position, and you'll have your other substituent, the less bulky one, as your axial substituent. In the other three cases, put both things equatorial and you will be fine. So this is kind of your cheat sheet here. So like on your homework, you've got dozens of problems on cyclohexanes, drawing the good one and the bad one. Or some you can just draw the best one. The best one will put your bulkiest thing equatorially. And if you can put both equatorially, by all means do so. So these are the relationships that we have here. All right. Just going to look at the homework real quick. So, for example, I guess, well, number 5, you're drawing chair conformations. And you're drawing both. You're going to draw the regular and the flip. And you're going to indicate the more stable one. But for something like number 3 on the homework, you can already figure out the most stable chair without having to draw both. It says trans 1,2 diethyl cyclohexane. Trans 1,2, according to this chart, we can put both equatorially. And therefore you should put both ethyl groups equatorially. In this case, it doesn't say if they're both up or both down, so you can choose, as long as they're both equatorial. I'm sorry, one is up, one is down. You can choose which one is up, which one is down. So that's what that means. Number 4 clearly has a typo. That one says draw your double Newman projection for your answer for number 6. That should be number 3, right? So number 3, you're drawing the most stable chair. Number 4, draw the double Newman for that. Number 5 now we can do. Number 6 we can do. 7 you've already been able to do. You've cried about that. Number 8 you can do now. Number 9, talk about ring strain and torsional strain. 11 we can do. By the way, with 11, if we look at those, so in number 11 we have some line angle drawn structures, and I'm asking you to draw some Newman projections for those, your least stable and most stable projections. So remember, your least stable will be the syn-eclipsed, where you have your bulkiest groups eclipsing each other, and then the most stable, you'll have them anti to each other, your bulkiest groups. In all of these, you're looking at the carbon, you're kind of looking down on those. 2 possible double Newmans for number 6. Let me look back on that. As in for, like, question number 4? Is that what you mean? I mean, it's okay if you draw both. Just indicate, just tell me which one's the better one. And so that should be the most stable chair, right? Because if you flip it, you're going to get both axial things. It doesn't matter if you draw both, but just maybe indicate which one correlates with the more stable one for your double Newman. So for 11, just to clarify, your eyeball is looking along the carbon-carbon bond that has all those wedges and dashes on it. So in each case for number 11, you have wedges and dashes on 2 carbons. You're looking along that bond, the bond that is between the carbons that have the wedges and dashes on them. All right, so you're going to be drawing those Newman projections there, and then you'll be having your chair conformations for number 12. For all of these, again, it would be a good idea to reference this chart that we have right here, because it's going to say, aha, well, that first one for number 12, those are cis to each other, and they're 1, 3. So I'm going to draw those both equatorially as my more stable one, and I'm going to draw them both axially for my least stable one. Okay, so just some hints on how to do it. So we're officially ready to do our homework. Isn't that so exciting? So we're pretty much good now. We are exactly where I want to be. We're actually a little bit ahead because we still have some time today. Let's see. Shall we dare go to try substituted ones? A little bit more complex. We could look at it. So if we're looking at a try-substituted one, it can get a little hairy. If we're looking at a try-substituted hexane, cyclohexane, things can get a little hairy, but this is kind of the, like, you'll kind of have some priorities that you may need to make. For a try-substituted, ideally all equatorial, if you can make them all equatorial, then that's the best. Right? If you can make all 3 groups equatorially. The next kind of, if we're going to do this in order, if you can't get them all equatorially, yes, in this case, yes, because they're all trans to each other, right? And we saw that 1-2 trans relationships, we can get them all equatorial. So for sure. So here, if I throw this then, aha. Now we can't. We are going to probably put that middle methyl axially in this case. So just depending on what you have, if you can make them all equatorial, that's the best. If you can't, and you can make 2 of them equatorial, make your bulkiest ones equatorial, if possible. If you can't, then get your 2 smaller groups equatorially. This is where this one gets a little hairy. Because if it's a T-butyl versus like a chloro and a chloro, you'd still probably want your T-butyl to be equatorial and have 2 chloros then axially. This one is kind of a maybe. This one is going to be harder to make that determination. If it's something super obvious, like where you have 1 T-butyl group versus 2 chlorines, the T-butyl is just going to be bigger, right? I mean, it's going to be far worse to put 1 T-butyl up than it is to put 2 chlorines up. So you'll have to... I mean, I'm hoping... I mean, I haven't given you any like this, right? But if on some forever reason you decide to look at some tri-sub cyclohexanes, that one could be a problem. So you kind of have to think if your 2 smaller groups, if you were to like add them together, are they bigger than your bigger group? And so generally, you know, if it's all the same, or if you have like methyl, methyl, ethyl, your 2 methyl groups are better to put equatorially and the ethyl group axially. But if it's methyl, methyl, T-butyl, probably T-butyl's got to go equatorially. So there's thinking required with this one. You have to think with number 3. Generally, your 2 small groups will probably be better to put equatorially. But maybe not. So just think about it. Be like, okay, well, I've got fluorine and fluorine. Fluorine is tiny, almost the same size as hydrogen. Is that really going to be worth an isopropyl group? Probably not. So, again, you might want to just have to justify that. And then that's kind of the last case there. So these are your best situations. So you're not going to have anything worse than this. Like, you're not going to put them all axial. Everything beyond those 3 is going to get less and less stable. So it just depends. So for this particular one that I've drawn here, ideally, yeah, you're going to have that middle methyl axially, and the methyl and chlorine then on 1 and 3 be equatorial. So, fun. Gotta think with these ones. But I haven't given you homework on those because I know that can be a little bit tricky. Alright, let's see. Anything else I want to talk about with this? Look at the end here. No, I should be good. Let's look at the back of the book here. Oh, how fun. We have some comparisons here. No, I think you guys have enough homework. I don't need to really go over more of these. We could, though. Do we want to do some complex problems? Why not? We have a little bit of time. Fine, we'll do it. So this will be number 67 from our book. We've got a Tetris-Substituted Cyclohexane. There's your crying already. Good. So, we can look at this first by analyzing the relative positions of our bulkiest groups. If we see our bulkiest groups on this are these 2, right? Isopropyl is our biggest bulk, and ethyl is going to be our second biggest bulk in this. Our third biggest would be the hydroxy, and then chlorine would be our last, right? So this is our biggest, second biggest, third biggest, fourth biggest for bulkiness. And so if we just look at our biggest, yeah, we can put them both equatorial here. We're lucky because those are trans to each other. 1,4 trans can give us some nice dually equatorial things. And so we're going to see as a result, we're going to have to put our hydroxy and our chlorines axially here. But what you want to do if you have a situation like this is compare your bulkiest groups, see their stereochemical relationship to each other or geometric relationship to each other. They're trans to each other. 1,4 is their position. We saw that trans 1,4. Aha! Wait a second. Oh no, trans 1,4. Yeah, both axial, both equatorial. So we're good. So let's draw it. Lightning bolt. Here we go. We can just kind of arbitrarily label these. I'm gonna do it this way because this is what I like to do. So that's those two carbons, and the rest just follow along in the ring. So I have an ethyl group that's up. Oh, this is a bad idea because that ethyl group, we want it to be equatorial. So I'm gonna switch this. Oh crap. Okay, let's see if I can fix my dots here. Okay, I'm gonna make the green one our methyl group. Oh, sorry, ethyl group, and I'm gonna make the blue one our hydroxy. Okay, now I can do things a little bit more nicely. So, with this, on our blue one, we have a hydroxy. We've decided that one has... Oh, here it is. Left things are 1. So isopropyls are... isopropyl is here. And our second biggest was ethyl, which is right here. I'm going to use a different color so you can see. That's why I chose isopropyl to be 1 and the other one to be 2. And then hydroxy will be 3, and then chlorine here is 4. So that's how I came to that determination. So this kind of, it's not really a chart, but it's kind of a chart. So I'll go with this for bulkiness. Okay, I'm going to erase all those green bits now, but that's how I have assigned them, those relative bulkinesses. Okay, cool. So, cool, yeah, no problem. We've decided that ethyl group and the isopropyl group can both be equatorial. So, if our ethyl group is going to be equatorial, I can put it there. It also needs to be pointing up with the hydroxy, so our hydroxy has to go axially here, because those two have a cis relationship to each other. They're both up. One is axial, one's equatorial. If we then look next, our purple carbon, 2 carbons away from the green one, we have a chlorine pointing down, which is going to be axial. And then if we see our isopropyl group has got to be equatorial and pointed down, that would be this position here. So we're going to have our isopropyl group there. That is the orange carbon. That's that orange carbon there. And the rest are hydrogen, so who cares? And in fact, this one is going to be our best structure, our best chair for this. Again, if you've rotated this chair, if you put your isopropyl somewhere, I mean, as long as it's the correct structure that has these 4 substituents in this relation to each other, where your isopropyl and ethyl are both pointing up equatorially, that's the goal. So if you've drawn the opposite one, you could draw this a little differently. If you wanted to draw it in the other way, you could say, okay, well, I'm going to make my ethyl group here. No, that's correct. And then I'm going to have my hydroxy group here. You know, whatever. It's the same structure. Where's our chlorine down here? These are all the same. These are the same structure. So if you've drawn it this way, it's exactly the same idea. So the point is that these relationships are together. So the oxygen, or the hydroxy and the ethyl are one carbon away, or they're adjacent rather. They're both pointing up. Oxygen or hydroxy is axial, ethyl is equatorial. Either way is fine. You can draw it, any way like this. So these are the same molecule. So I'm not saying you have to draw it exactly the way I do. I just prefer, it's my preference, the way that I've done it forever, is I draw my cyclohexanes usually like this. Some people draw them this way. This is their standard cyclohexane, where they have the pointy bit in the top left. I like my pointy bit in the top right and the bottom left. So that's my choice. You can do whichever one you like. So both of those are the same structure, though. Hopefully we see that. They're just kind of shifted slightly. They're not flipped. This is not a chair flip, but this is a different way of drawing the same molecule. So not flipped, but just, I don't know, rotated, I guess. I've just basically shifted everything that way a little bit. So your choice. Whichever way you like to draw your cyclohexanes, if you like thunderbolts like that or thunderbolts like that, whichever one, you're good to go. These are the same structure. Okay, but again, important things with this, things that are on wedges are pointing up. Things that are on dashes are pointing down. And if you forget what those positions are, up we go, up we go. Aha! All the green ones are pointing down. Those would be on dashes. Everything that's light blue here is pointing up. And those are wedges. So don't forget that sometimes, it may not seem up to us. Like this one right here, it may not be obvious to us that this equatorial one is up. But it is. Trust me. That one is up. It's easier to see just like the axial things, right? The equatorials can be a little bit tough to see up and down because they're much slighter angles. But trust me on this. For this, these are all the up positions in blue. All the down positions are in green. So everything that's on a dash should be on a green line here. Everything that's on in a wedge should be on a blue line if you're drawing your cyclohexane like this. If you have the other one, they're all just flipped. So, but if you have your pointy end in the top right and bottom left of your molecule, you're going to have these particular ups and downs. Okay, cool. So that's how we would draw that one. Any questions on this particular molecule? We didn't have to think much about this. We could see that very clearly. We had two very bulky groups. We need them to both be equatorial. Let's see. Any other good problems here? Interesting. So, what other ones can we do? How about just some for fun stuff? Just some tidbits here. Let's talk about glucose. There are very, very many constitutional isomers that we can make out of glucose. That formula, C6H12O6. 16 of them happen to be 6 carbon sugars. So there are, for this particular thing, 16 6 carbon sugars. Typically, we see glucose, galactose, and what's the third one that we see? Glucose, galactose, and maltose is 2 glucoses. Glucose and galactose is lactose. Mannose is the third one, right? No, fructose is another one, but it takes a 5-carbon ring. So it makes a 5-membered ring, so... or maybe that is... Is fructose the one I'm thinking of? Is mannose... No, mannose is a 6-carbon sugar. But anyways, we have all these different 6-carbon sugars. And they all have... these ones at least have 6-membered rings. Fructose has a 5-membered ring, so we're not going to worry about that. But the reason that we always talk about glucose and why glucose is kind of our main energy storage unit in biological systems is because with glucose forms a 6-membered ring. And we often draw it in a Hayworth projection where we have things pointing up and down. So we're looking... Yeah. This is ideally the way that glucose looks. With the other 6-carbon or other sugars, this is all like, I'm not going to test you on this stuff. This is just for fun because we're talking about these chair cyclohexanes. We'll see why glucose is ideal with this. And in fact, the better position is beta glucose. Technically, glucopyranose is the way to talk about this, but glucose can be a linear structure or it forms this ring structure, preferably. What's interesting though is we see that things are kind of all trans to each other, right? We have these hydroxy groups that are up and down alternating. And what actually happens with these is we end up... The reason that glucose is our kind of ideal sugar is if we draw this, we see that all of those hydroxys become equatorial. And this one is going to point down. So all these hydroxy groups in beta glucopyranose, the 6-membered ring form of glucose, all have equatorial positions. Actually, let's go ahead and let's see, chair conformations of sugars. Let's see if we have some good images here. These are all glucose. Aha! These are kind of ugly, but suffice it to say, look, let's look at Wiki or Google for a second. Let's put that up. Cool. Okay. With this, if we see... Oh, here, let's look at this one. Here are all these different sugars. Oh, look, they're even on Wikipedia. Perfect. Okay, let's zoom in. Oh my god. I'll donate later. Stop yelling at me. Okay. Look at all of these sugars here. So with these 6-carbon sugars that we're looking at here, glucose has everything equatorial. They put these squiggly line ones because that particular hydroxy can go either direction. We call one of them alpha if it's pointing down and beta if it's pointing up. So beta glucose here would point up. But here's our glucose, where everything is equatorial. Our other sugars, mannose, galactose that we see, they all have one axial substituent. And as we add more and more axial ones, they become less common, because who the heck has heard of altrose or allose or gulose? Who the hell's named this gulose? Glucose and gulose. Like, whatever. The point is all of these, though, we see glucose is our most stable one because we have everything equatorial. With these other sugars, we have axial positions, and so they become less common for us. And so, as a result, biology favors glucose, which is why we see that so often. So, rather than gulose, unfortunately. So we are not in a gulose-based biology, we are a glucose-based biology. So, no axial ones for us. So just changing the directions of those gives you a new sugar. Those are stereoisomers of each other. And so we can throw a little biochemistry into this stuff too. So we're not just totally going crazy with the cyclohexane business. There are real implications for having all equatorial positions. That makes it stable. That's going to be the reason why glucose is our preferred sugar. So, hooray. And not glucose. So suffice it to say here, glucose is better than gulose. What a funny name. So cool. Gulose, I think, had those last two axially drawn. So gulose was this guy. I might be mistaken, but gulose had two axial ones. It's the knockoff version. Yeah, you go to the if you buy it on wish.com, you get gulose instead. That'd be fun. Interestingly, though, biologically, they do taste the same, supposedly. Gulose and glucose. So, I have never tried it, but there you go. So there's our gulose and our glucose, and so there they are. So that's the reason glucose is more stable. That's why we use it, biologically speaking. We're going to see that this is D-glucose. L-glucose has everything axial. And so, like, L-glucose is kind of the worst way to make it. But that's for another time. We'll talk about that next semester. We'll talk about different types of sugars, so, and the chemistry thereof. So, since we had a little bit of extra time, I think we could talk about biology, see some relevance here, that we're not just talking about shares for no reason. So, cool. Alrighty. Any questions on these? Any of these conformations? Let me just look. When's our first exam? It is, oh goodness, it's Monday. So, when do I have this homework due? Let me just check real quick on Canvas when I have your homework due. I need to get your homework keys up as well, but we'll worry about that later. Okay, so with this homework, it is due the 22nd. I do want you guys to see the key. Should we push our exam to some other date then, perhaps? Do we want to just do the exam on the 27th? Would that be better? And give you some extra time to process this sort of stuff? I think that would be useful, right? Okay, let's do that then. Either way. Yeah, so it's either move the homework due up earlier, but I don't want to do that because it's pretty long. So, I mean, I guess I could do a poll on it either way. So either the homework we do the 18th, 3 days from now. Yeah, I think you probably just want more time. So for this exam, I'll just push it back a week. And it'll still cover the same stuff, so we won't talk about stereoisomers when we talk about this one. So we'll push the exam date so you have more time to finish this. So you'll turn in your homework on the 22nd, and the key will be available then somewhere over the weekend, and then the 27th we'll have the exam. And so we'll just go from there. Okay? So I'll do an email on that as well, but we're going to push it to 9/27 then. All right? And so we'll have that. So it's still chapters 1 through 4, which is everything until now. Oh, and I guess I should give you guys some practice exams, huh? I'll put those up as well, so you can see what kind of nonsense we're getting into. Actually, I can maybe show you one. Let me see if I've got one on this computer. I do. Okay, let's take a look. So, your exam should be somewhat similar to this. For example, This one's talking about kind of the stuff we did in the first week, where we talked about, the number of lone pairs, the numbers of sp3 hybridized atoms, talking about oxygen B, talking about its hybridization there. So stuff like this will definitely be on there, where we're talking about various hybridizations and bond angles and geometries and how many sigma bonds we have, what's the formula of this thing, etc. So obviously you guys aren't in Chem 105. That is the numbering that it used at my previous college, so you're in 221. But this compound should give you nightmares regardless. And we're just seeing examples of that. You'll have some nice resonance ones. For example, talking about starting resonance by moving bond A. What can we do to make that resonate? What's kind of our best resonance form? And then comparing the resonance form you get for A to the original molecule to resonance form B, seeing what you can do with those. All right, talking about some acid-base stuff. What's more stable? Which is the kind of the direction this reaction is going to go, and why? If we're going to redraw a molecule in various projections, I'm probably not going to ask you Sawhorse on this exam because I'm going to do that more in chapter 5. But I could certainly ask you Newman. That's not a problem. You can say, okay, well, is this thing going to be, like, which way did you draw it? Did you decide to draw it eclipsed, syn-eclipsed, gauche anti? Let's draw some more Newman conformations. So whatever you happened to draw here, let's rotate it in certain degrees and see what happens here. Let's talk about what has the least strain, which was the closest one to anti. Talk about which one's more acidic, comparing these things. Yeah, it'll be just like this, Jackson. I think you're Jackson, right? Just very much like this exam is right here. The only stuff that we're talking about. We can talk about some naming structures. Ooh, we didn't talk about bicyclics, did we? Did we talk about bicyclics? I don't remember. Draw some chair conformations. So it's basically everything we've done up till now. Does anybody remember if we talked about bicyclic structures like this middle one here for number 6? Do we have we talked about how to name those? Maybe. I'll do it just in case because I don't think we have, or we spent very little time on it, so maybe we should do that real quick. Oh, right, because I did talk about naming cycloalkanes, but they weren't bicyclic. That means there's 2 rings. Okay, yeah, it's in the book, but it's not too bad. So something like this. Can be visualized in, this is kind of a like, okay, yeah, this is a like kind of 2-dimensional drawing of it. It could also be drawn this way, where it's a little bit more 3D. So you can see here we have kind of 2 rings at the same time. We have the first ring in green, and then we have the second ring in blue. Some of these are the same, so we're going to see that 2 of these are the same. These are both blue and green. There, that kind of middle one. The way we name this is we want to look for what are called bridgehead carbons. And those are the carbons that are going to be part of both rings. So, or rather the ones that kind of join the 2 rings. These are what are called bridgehead carbons. And so when we're naming these, we're going to be looking at kind of everything that's attached to those bridgeheads. So the bridgeheads are the shared carbons there. And we're going to basically look on all three sides of those bridgeheads and see how many carbons we have. On the green side, we have 1, 2 carbons there that are on the green side. Yes, Kevin's got the right answer, as always. On the blue side, we've got 2 carbons. And then on the like kind of half green, half blue side, in the middle there we have 1 carbon. It's both. It's shared between both. How we will name this is we are going to name it starting with kind of the biggest number of carbons, whichever side has more carbons than the other. We're going to name it that way. And we're going to name kind of in biggest to smallest how many carbons are in each section. And then we're going to count them all and make that our parent structure. So for example, we have the green ring has 2 carbons, the blue ring has 1, and then we have that kind of 1 shared one. So we'll call this 221 just to indicate how many. It doesn't matter which 2 you put first. I put the green one first, you could put the light blue first, doesn't matter. And we're going to want to number these. We want to see how many carbons we have all together that's part of both rings. And so for this one, we're going to see that we have, this will be a cycloheptane. We have 7 carbons total in the structure. Let me see, do I have a good... This is all about like thing. Let me see if I can get some more examples from our book here. Yeah, we can do 3 through 1. Yeah. So with these, how these are numbered, by the way, you'll start at one of the bridgeheads and go your longest path to the next bridgehead. So if I decide, let's do one that actually has more than 2 carbons, ones that actually have different sides. So if I do the same molecule, but I'm throwing in a 3rd carbon now, or a 4th one, I don't know, we'll see. If we look at our bridgehead carbons, those are those 2. We're going to see how to number these and how to figure them out. So I'm going to do the same thing. I'm going to have a green ring. So I've got 1, 2, 3 carbons in this green ring. And I'm going to just leave the black one alone. 3 rings in that section, or 3 carbons. I've got 2 carbons in this blue section. And then I just have 1 carbon in the black section. So if I'm going to number these, I could start at either bridgehead, doesn't matter which. That would be carbon 1. So if there are substituents on these. How we number these is we are going to start at one bridgehead and we're going to kind of go along our longest path first. So that's why 2, 3, and 4 are in the green ring. Then we're going to go to our next longest, which is 6 and 7. And then we're going to end with our smallest one. So this is how we would name this. So if we had substituents on here, if we say had a methyl group, on this, let's put another one on carbon 3, or let's put one on carbon 2. Why not? We've got some methyl groups on here. Our parent name is going to be this bicyclic structure. If we didn't have the... Okay, let's get rid of the methyls. Let's just name this as is. We're going to name this 3.2.1. Oh, I didn't put bicyclo in here. Or do I need to put Yeah, I do need to put bicyclo. Yeah. We're going to put that in parentheses. bicyclo, because this is 2 rings. And we see there are 8 carbons altogether. So we'll do a bicyclooctane here. Yes, you can put the 321 in between. You can do this. We're going to see it'll be the same thing when we're talking about like alcohols. We could say this is 1-propanol, although it is technically better to say propan 1-ol. We're going to see you can kind of stick the numbers where you like. It's kind of easier to read if you put the numbers first, but it's more correct to put the numbers in the middle of the word. So Kevin's answer is more like IUPAC correct, though you'll also see it written with the numbers beforehand. So they do both. You'll see both. Right. So we'll be correct though. We'll do it the IUPAC way. Kevin is always right with these silly structures. Okay. If we want to put substituents on there, boom, boom, we would say 2,8-dimethyl bicyclo 321 octane. Ta-da. Yes, ideally, yes, you'll put the numbers in the middle. That is the kind of like preferred method for IUPAC. But IUPAC sucks, but we must learn it that way. So we'll be consistent. We'll be good with our IUPAC nomenclature. So that's going to be the way we do it. So if we started numbering from, what other colors do I possibly have here? Orange. I could have started numbering from this and done it this way. Although now with these methyl groups, I cannot do it the orange way, because that's going to give us bigger numbers. We'll get 4,8-dimethyl bicyclo 321 octane. So in this case, because we have substituents, we want to start numbering from the one that's closest to the substituent on the longest part of this bicyclic structure. So, sorry. So in this case, we have to use the purple numbers. The purple numbers are the right way to go, because they give us the lower one. If we did the other one, we would get 4,8-dimethyl bicyclo 321. Oops, we don't need that extra dot there. Octane. So can't do that. That one's wrong, because we want to give our substituents the lowest numbers possible. Right, so 2 and 8 is going to be the way to do it here. So, all right. So that's the best way. All right, so not that one. Okay, that's bicyclics. Cool. So next time, we're going to end a little bit early today. We go to 12:15, yeah? Yeah, we do. Next time we're going to talk about what's called stereochemistry, which is going to be a way for us to distinguish naming these two. Because these are going to be, in fact, different molecules. We're going to see a way to name these so that we always know which one we're talking about. Because geometrically, these two are not the same. We have a wedge hydroxy versus a dash hydroxy. These are going to be different. They're going to have different properties. One will actually bend light a different way than the other one will. We'll talk about that. So I would strongly recommend reading ahead to Chapter 5 now that we have a little bit more of a break between our exam. And start that. I'm going to teach you some techniques for dealing with stereochemistry. We'll still have the review on Friday, and we can do another one next Friday. That's fine. That's cool. Speaking of which, let's check. What are we? So it looks like 10 o'clock is going to be the better one for that. So 10 o'clock on Friday, we'll do a review, and then we can do another one the next Friday. So we'll still have, so fine, that's Monday. Review. So Friday at 10 to 11 on Discord. So you're gonna just come into, there's a a classroom voice chat. We'll go there so you guys can ask questions more directly. So you'll join, you'll like kind of click classroom under C221. So like I'll do it right now. Poof, there I am. So you'll see that's where I am now. I've just clicked classroom on Discord here. Why am I not showing you? I'm not showing Discord right now. Okay. Let's see. Aha, here I am. So, cool. If I wanted to say on Friday I'm coming to the review session, all you have to do is click classroom. Ta-da! And you'll see that I will have my screen sharing, and so when it comes time, you'll just click my name when you see the here. I can maybe even do it. Let's see. What can I do? I will show Discord. I'm streaming Discord. When you see this live thing by my name here, what you'll do is you just click it, and then you'll be able to see my screen. Now I'm showing myself showing the screen, so we have now an infinity mirror type of situation thing, but that's what you'll do to watch it. And here you can then just talk and do that. There are some buttons here. Mute yourself if you want. You can deafen yourself. I would never recommend that because that just means you can't hear anything. So not a good idea. So when you see this live thing, just double click my name. To get in the channel, you just click classroom, and that'll get you in. All right. I'll make another channel now for review questions. So here, just post stuff that you want us to go over. Say, hey, number 12C on the homework, I'm really having trouble. Can we please take a look at that, or whatever, just something like that. Post screenshots. Ideally, if you can't post a screenshot, at least be super descriptive, or say, hey, can we do another example of whatever. Just do stuff like that. Okay? So let's disconnect this. And I'm going to, oops, just mess that up. Let's go back to seeing my face. Ta-da. So that'll be Friday. I hope I remember. If I'm late, which I shouldn't be, I'll put an alarm, but just ping me if I'm not there, and I'll show up. So, all right, cool. I will record that as well. It'll just be on YouTube. It won't be on Twitch, because if you guys want to ask verbal questions, it'll be harder for me to do that on Twitch. So it's just easier if we do it in Discord, and I'll just screen cap that. So we'll still have it for people who can't make Friday at 10. So we'll still have that. Okay. Awesome. I think we're good then. So I'll send out an email that I've pushed the exam back 1 week. So it'll be on the 27th. So your homework will still be due on the 22nd. I'll put some practice exams up. I'll hopefully have those for you. I'll try and put them up today. Wednesday is my busiest day of the week, so maybe it'll be tomorrow or Friday. And I've got to get your... I'll try and put it tomorrow so that you can actually look at it before Friday. So if you have questions that you I have no idea how to do this, we can at least address those this week. And I'll get your homework key up for your last homework set as well. So I've got a busy week. So I'm moving right now too. So I'm in a house that has very little furniture. I'm on a plastic desk now, and it's a mess. So just give me a little leeway here. So thank you for your patience on that. But I'll get those. As you know, I'm a terribly slow grader, but you'll at least have the answer key soon enough that you can compare with. So, all right, cool. Awesome. Thank you, guys. I guess we'll see you on next week or Friday. So, awesome. Okay, take care, everybody. Enjoy your next couple of days. Take care.